In this lesson, we're going to talk about several gas law relationships. There are names to these relationships, and they're named after scientists who discovered them. Charles's law relates volume to temperature for a gas. Lussac law relates volume, or pressure to temperature for a gas. And Avogadro's law relates volume to the number of particles for a gas. Let's start with Charles's law first. Take a look at this picture. We have two containers of a gas. The pressure is the same in each case, 1 atmosphere. But in the container on the left, the temperature is 200 degrees Kelvin. In the container on the right, it's twice as much. The volume also expanded from half of a liter to 1 liter. So as the temperature doubles, volume doubles. Gases occupy greater volume at higher temperatures. Now, before we get into the mathematical relationship, which is helpful, we need to talk about how we express temperatures related to gases. This involves the Kelvin temperature scale. As temperature goes down, we know that gas particles go slower. Eventually, they'll condense into the liquid state. And if you continue to lower the temperature, they'll freeze and enter the solid state. Even within the solids, the vibrational motion goes down and down and down until eventually it stops. The temperature at which vibrational motion stops is called absolute zero. And that occurs at negative 273 degrees Celsius. Lord Kelvin, after whom the temperature scale is named, simply took a degree Celsius and renumbered it. If you take, and I should point out, it's actually impossible to achieve absolute zero on Earth. We can get really, really cold. We can actually, with more recent experiments, we can get within a fraction of a degree Kelvin of absolute zero, but you can never actually get there. So the way we figured out what absolute zero was is by graphing volume versus temperature and looking at the x-intercept of that graph and seeing that that x-intercept is approximately negative 273 degrees Celsius. Lord Kelvin just said, let's keep that same graph, but we're going to renumber the degrees from 0 on upwards, such that it's impossible to have a negative number of degrees Kelvin. One other thing that's interesting about the Kelvin scale, we don't, when abbreviating it, we just use the capital letter K. There's no degree sign. Okay, that brings us to Charles's law. Charles's law says the volume divided by a temperature initially is equal to the volume divided by the temperature in the final conditions. This is much the same format as Boyle's law, where the subscript 1 refers to initial conditions and the subscript 2 refers to final conditions. But whereas Boyle's law was written as pressure times volume equals pressure times volume, this one is divided by, and that makes a big difference. When using Charles's law, you have to convert all the temperatures into degrees Kelvin, and that's before doing the calculating. Sometimes students say, well, I'll convert to Kelvin, but I'll do it after using Charles's law. That's not good enough. You need to convert into Kelvin before using the formula. Now, you might say, why? What's the point of making that temperature conversion? Because I remember in one of the sample problems related to Boyle's law, it didn't matter whether we used units of atmospheres for the pressure or units of millimeters of mercury. Why can we get away with that in Boyle's law, but with Charles's law, you're insisting on a particular version of temperature degrees? That's because of the relationship between Kelvin and Celsius. To convert between those two, you're either adding or subtracting 273. You're not multiplying or dividing. They call that type of a relationship in math class an arithmetic relationship, whereas the other type was called a geometric relationship. The kind where you're multiplying and dividing, it's less important to make the unit conversions before using the formula as it is with an arithmetic relationship like temperature. Okay, with Charles's law, we saw that gases occupy greater volumes with increasing temperatures. That's what's called a direct relationship. It looks like the line y equals x. And that's because when you divide volume by temperature, it equals a constant number. Let's try a short practice problem, and then we'll come back to the slides in just a moment. If a sample, oh no, wait, we want to do the Charles law one. 2 liters of oxygen gas at 100 degrees Kelvin is heated to 400 degrees Kelvin. What will be the new volume? Let's first write out Charles's law. V1 divided by T1 equals V2 divided by T2. And let's identify those variables in the description from the problem. And at first, we have 2 liters and we have 100 degrees Kelvin. Those are the initial conditions. So let's put the 2 liters on top and the 100 degrees Kelvin in the denominator. Conveniently, they gave us the temperature in Kelvin right off the bat. We don't have to worry about converting. They tell us the final temperature of 400 Kelvin, but they do not give us a final volume. So let's leave V2 as the unknown variable to solve for, and 400 degrees Kelvin will plug in for T2. You might remember from math class, if you want to get a variable alone, you have fractions that are equal to each other, do some cross multiplying. So we'll take 2 liters times 400 degrees Kelvin, and we'll set that equal to 100 degrees Kelvin times V2, the unknown variable. We then will divide both sides by 100 to get V2 alone. And then you might be able to do this in your head, or if not, feel free to use a calculator. 2 times 400, that's 800. And then we divide that by 100. V2 works out to be 8 liters. The reason I know that the volume unit will come out in liters is because that was the volume unit that V1 was given. It gave us liters, and so the answer will come out in liters as well. Okay, that was a nice, easy application of Charles's law. Let's continue. The relationship between a gas's pressure and temperature was first described by a scientist named Gay-Lussac. He noticed that as molecules move faster in a sample with higher temperature, they'll collide with the walls of their container with greater force. That increases pressure. Mathematically, Gay-Lussac said, P1 divided by T1 equals P2 divided by T2. This looks almost the same as Charles's law. It's just that we're substituting P's in the place of V's. And just like with Charles's law, all the temperatures need to be converted into Kelvin before using the law. That is, do the converting before you do the calculating. Just like Charles's law, if you were to plot pressure and temperature against each other, you would get a straight line that proceeds from lower left to upper right in quadrant 1, just like the line y equals x. Let's do a problem that illustrates Gay-Lussac's law. If a sample of a gas has a pressure of 150 kilopascals at 20 degrees Celsius, at what temperature would it have a pressure of 325 kilopascals? First, let's write out Gay-Lussac's law. And it is a-okay to work in kilopascals. You don't need to convert into atmospheres or millimeters of mercury. Just leave it in kilopascals for the pressure. But if you remember, we have to convert the temperatures into Kelvin. So let's take 20 degrees Celsius and add 273. Kelvin temperatures always look like really high temperatures because at least from everyday experience, we're used to temperatures that are below 100. Well, how about 293? That's pretty high. Or it seems pretty high, but it's actually room temperature roughly. So if we add 273 to 20, we get 293 degrees Kelvin. All right, let's put this together. the initial pressure was 150 kilopascals. Our initial temperature after converting into Kelvin, 293. The new pressure is 325 kilopascals. And the new temperature is unknown. Just like Charles's law, to get the variable alone, we're going to do some cross multiplying. So we have 150 kilopascals times the unknown temperature T2 is equal to, and you might want to pull out your calculator here, 325 times 293 is 95,225. So to get T2 alone, we're going to divide both sides by 150. And we get T2 equal to, after we divide this out, we get roughly 635 degrees Kelvin. Now, notice the temperature comes out in degrees Kelvin because the input in the formula that we used was in degrees Kelvin. If you had input something in Celsius, it would come out in Celsius. But to prove the point that if you failed to convert into Kelvin before using the formula, you'd still get the wrong answer, I want to show you what 635 Kelvin looks like in Celsius. So if I take 635 and subtract 273 from it, I get 362 degrees Celsius. If we had failed to convert into Kelvin and we used Gay-Lussac's law with, let's say, if we had improperly put 150 Kelvin over 20 and set that equal to 325 over T2, we would have arrived at a temperature, T2 would have worked out to be 43 degrees Celsius. And you could add 273 to that and get the equivalent temperature in Kelvin, and it would work out to be 316 Kelvin. The fact that this temperature, 635, is not the same as this one, and 43 degrees Celsius is not the same as 362 Celsius, tells us that this approach is incorrect. That's why you have to convert into Kelvin beforehand. So the correct answer is either, and I don't mind which final temperature unit you use, but it has to be either 635 degrees Kelvin or 362 degrees Celsius. Okay, there's one more gas relationship we should talk about, and that's the relationship between the number of particles and volume. Take a look at this picture. We have two gas samples at the same pressure. In one of them, there's 1 mole of particles, and it occupies a volume of 22.4 liters. In the picture on the right, there's twice as many particles, occupying a volume of 44.8 liters. It was the scientist Avogadro who reasoned, as more molecules crowd into a sample of gas at constant temperature, they'll collide with the walls of their container with greater frequency. Not more pressure, but greater frequency. As a result, if you want to maintain a constant pressure, you've got to space them out more. And so that means the volume goes up. V1 over N1, where V stands for volume and lowercase n stands for the number of moles of particles, equals V2 over N2. Number of particles in a sample is counted in, of course, moles, and we abbreviate it with an N. If you were to plot this relationship, Again, just like with Charles's law and Gay-Lussac's law, you would get a straight line proceeding from lower left to upper right. It's a direct relationship. With that, you're equipped to handle our homework tonight. Good luck with that, Steve.